thanks for coming. Yeah, I was just saying that, yeah, I mean, like the time, I don't know if it works for everyone, but I mean, like if someone has some serious difficulty, then I mean, let me know and we can try to adjust. So I'll hand it over to Saravanan, but just before I do that, I just wanted to let you know about the schedule that we have so far. So yeah, so I think I've updated the web page. So yeah, so it's Saravanan, and then next, so yeah, so basically 2 weeks from now, we won't have a talk because of the SODA deadline and ICML. So the week after, on 24th July, Raghav Adanki will give a talk on his recent paper on intervention design for causal discovery. And then Sutanu, who has been working with me here at NUS, he'll give a talk on weighting-based estimators based on a paper by Tian and Barenbaum and Gian, I think. And then after that, on 14th August, so Andrew Elias, who has been working with Costas, so he will give a talk on inference with truncation. And then, yeah, and then also, I mean, so some other people have expressed interest, but if you want to give a talk, then just let me know. I mean, this doesn't need to be an advertisement for your own talk. Like, for example, the talk today is going to be by Saravanan on some older stuff. So, I mean, if you want to discuss something, then feel free and let me know. Okay, so with that, I'll hand it over to our speaker today. So, let me stop sharing. Yeah, so our speaker is Saravanan. So, he's a PhD student at Cornell. So, he's, I mean, he was a master's student with me a few years ago. And so we started working on causality, and it's interesting that his interest has still carried on. So Saravanan today will talk about causal identification. Okay, so I'll hand it over to you.
Yeah, thank you, Arnav, for the introduction, and thank you for providing this opportunity. And thank you everyone for being here. So today I'm going to discuss this paper by Huang and Valtota. Let me set up my screen. Okay. So the title of this paper is Completeness of an Identifiability Algorithm for semi-Markovian models. So this is by Emin Huang and Marco Valtota. So first of all, I would like to apologize for my poor handwriting. It's not so good in my OneNote. And secondly, I would like to tell that we will actually not discuss this paper as such. So the main result of this paper is the completeness result. And the completeness result is quite convoluted in the sense that it's like a 25 pages combinatorial result, which involves several case-by-case analysis. And it also requires introduction of what is identifiability and what is an identifiability algorithm that has been established before, and so and so, so and so. So instead, what we actually do is so basically what I will do is I will explain the identifiability algorithm that was established before this paper, prior to this paper was published, and I will just describe what this paper has done. And so this is basically the picture. So there is this algorithm one, call it. So this is identify probability of S given do of P minus S. I will describe this formally later. It's also notated. It's also denoted by Q of S. and there is this algorithm 2, which is a more general version of the previous algorithm, and this is identify P of S given 2 of T. And what this paper has done is to provide completeness part for both these algorithms, especially the second algorithm. And these are basically constructions that provides counterparts to these two algorithms. And this algorithm 2 was by Ian and Pearl in 2002. And the
Certainly, we're
constructions.
going to define PS, do T, etc. Right?
Yeah. I will define everything. I'm just giving the picture right now. Yes, I will define. And so this completeness part actually was established by Spitzer Pearl and also by Huang and Valdota, this which is this title in 2006. So both these papers won student best paper award in AAAI 06, and this paper by Huang and Valdota also got published in Annals of Mathematics and Artificial Intelligence in 2009. So what we will discuss is algorithm 1. We will skip algorithm 2, and we will not discuss these completeness results. Okay. So the goal of this discussion is to have a solid understanding of fundamental concepts, and also to understand this algorithm 1 to a good extent. And this is a relatively easy topic to understand, and so in case if you miss anything, please feel free to interrupt. It is my mistake than your mistake, so please feel free to interrupt. And it's also slightly hard to explain within 1 hour, so I will not explain with illustrations or examples, but if people interrupt, then definitely I will bring up examples to explain the concepts more clearly. With this being said, I will first describe the agenda. So the first part is basic definitions. This will be the first 15 minutes, and then the second part is the identification, introduction. Third part is several observations in the form of theorems and lemmas, and then the fourth part is that we will culminate into the identify algorithm. So this is the rough agenda divided into 15 minutes each, but please feel free to interrupt. I will squeeze in a little bit and give a complete picture in 1 hour. I will try to do that. So let's first discuss the basic definitions. First, I will describe what the model that we are interested in. So the model is called as causal Bayesian networks, also known as structural causal models. It's a very easy model to describe. So the model consists of some random variables, which partitioned into V and U. V the observables, U the unobservables, and all these random variables are discrete. They take value from a finite alphabet set, and the model also consists of a causal graph, also called as acyclic directed mixed graph. So the causal graph.
Paper, sorry, interrupt. I mean, the setup doesn't require discreteness, right? I mean, it could be.
It could be random, but for identifiability, we need discreteness. Otherwise, I don't know how to define identifiability as such.
Okay.
I mean, obviously, like there is an equivalent definition of identifiability for continuous models, but I don't know any results in the continuous domain.
Okay.
and the causal graph is a DAG, and this directed acyclic graph is only on the observables. Think of it that way. And there are unobservables, ui. So this ui is a singleton and u is a set of variables. And these unobservables satisfy some specific property in the sense that these unobservables have, ui has no parent and it has exactly two children. So I will explain this with an example here. So consider this example where there are three variables, v1, v2 and v3, and there are two unobservables, u2 and u1. Okay, and these are the arrows, let's say. So the u1 has exactly two children and u2 has exactly two children. So that's what I mean by has exactly two children. And u1 and u2, they have no parents. So that's what I mean by has no parent here. And it's a DAG on the observables. V1, V2 and V3 is a directed acyclic graph, right? So this is how the graph is defined. So more general graphs where the unobservables have parents and they have more children can be reduced to a graph of this form, such that several important properties are maintained. So I'll not get into that discussion here. For today's discussion, we will assume that the graph respects this property. And the model along with this graph, it also contains a set of local distributions. So the local distributions are, the first one is for unobservables, probability of ui for each I or for each ui in u. So this is the first set of distributions, and the second set of distributions is for every variable, observable variable, and for every assignment to the parents of certain observable. So here by parents I mean like including unobservables. So like where A is an assignment assigned to the parents of Vi. So there is a corresponding local distribution associated to this A parents of Vi. This distribution is on the variable Vi. Okay, so far so clear. So now once this model setup is ready, the observational distribution and interventional distribution can be computed. What do I mean by that? Let me explain this for this example just to make it clear. So for this example, the model has a distribution probability of ui for I in 1 to 2, and the model has probability of v1 given assignments to u1 and u2 for every assignment a, where sigma is the alphabet set, and for v2's parent is u2, so u2 every assignment to u2, and v3 has three parents u1, v1 and v2. So these are the local distributions, and this is the graph G. And so then like provided all these things are defined, we will be able to write down the observational distribution v1, v2, v3 as follows. So this is the marginal over the unobservables u1 and u3, and let's call this a v1 v2 v3. Just for some assignment I'm writing the probability, and this will be probability of u1 multiplied by probability of u2 by probability of v1 given the parents of v1 u1 comma u2 multiplied by a v1 v2, and this is v2's parent is u2 and v3's parents are u1 v1. So what happens is that you think of this each variable as an entity or a human being, for example. So what this human being does is he or she looks at their parents, and the parents are set to something. Okay, the parent is a u1 u2, for example here. Then v1 will take values from this distribution for that corresponding assignment a u1 u2, and then it will basically think of that as a random event, and then v1 will choose its value, and then this process continues because it's a directed acyclic graph. This distribution is well defined. So this is the observational distribution, and now I will introduce intervention. So for example, let's consider this intervention do of a v1 v2. So here this notation means that v1 and v2 are set to this assignment a, I mean a v1 v2, and so what this means is that look at the causal graph. So this is v1, and this is v3. So v1 is forcefully set to this value, and v2 is forcefully set to this value irrespective of their parents, and u1 will have an edge from u1 to v3, but u1 does not have an edge from u1 to v1 because v1 is like forcefully set. And so this will be the induced causal graph upon this intervention do of a v1 v2, and the distribution that we get would be probability of v3 given do of a sub v1 v2. This is the notation that we use for interventional distribution, and this will be summation over u1 probability of v3 given a v1 comma v2. So the summation is u1, right? u1 multiplied by probability of u1. So this is the natural definition. We are just marginalizing over u1 because we don't really care or we don't really observe the unobservables. So yeah, I'm just not writing the unobservables on the left hand side. So this is the definition for intervention. Like I will not.
Question from Janaki. So can you repeat what do notation stands for?
Yeah, so the do notation basically says that the variable, so in this example the do of a v1 v2, this means that the variables v1 and v2 are forcefully set to these values. So this more, so basically what we do is like these randomness, right? So here these two randomness, we basically substitute these two, we basically remove these randomness from the model and we substitute them by constants. So in this case the constant is a sub v1 and a sub v2, and the rest of the variables behave based on the model, based on these local distributions. So it's do is basically an external action that we forcefully set. For example, in this coronavirus pandemic, for example, we are uh, basically we want to understand how this virus behaves, so we might inject this virus into people who have been vaccinated and test whether the vaccine works or not, right? So here, irrespective of how they are going to get the coronavirus naturally, we are forcefully injecting the virus into such random trials, right? So basically any external action that we do voluntarily that deviates from the natural behavior.
So Clement is asking, is there a difference between this and conditioning? Or is it the same thing but
Yeah, I will come to that. There is a difference between this and conditioning. I will come to that in like a couple of minutes. Okay, so this is like in chat, is it? I'm not able to read the chat, sorry. Or am I unable to hear Clement?
Yeah, sorry. Yeah, that was in the chat.
Oh, okay, I see. Cool.
Thanks.
Okay. Yeah, so this is the definition of intervention. Thank you. And now we will move on to more formal definitions of observations and interventions. So once this model
I
is
think,
defined,
before that, you can just give a simple example, right? Even with two variables, that conditioning and intervention are different.
okay, yeah, sure. So, uh, so, so look at this example V1, V2. So here, so this is the graph, and the observational distribution is probability of V1 and V2. So here, the probability of V1 given 2 of V2 is equal to conditioning probability of V1 given V2. Perfect. However, in the same example, in the same graph, the probability of V2 given 2 of V1 is equal to probability of V2 based on the model definition, because it doesn't matter what whether we set V1 or not, V2 is going to behave the same way because the local distribution is probability of V2. So yeah, in some case this is conditioning, in some case this is not conditioning, right? This is a very trivial example. There are like other complicated examples which we might see later.
Thanks.
Okay, thank you. Okay, so just for completeness, let me formally describe these two distributions: observational distribution and interventional distribution. So the model is well defined. The observational distribution is for any assignment to the observable variables. This will be the marginal over all the unobservables, and this will be for every observable product of observable given the parents of the non-observable parents of vi. This will be pys. So basically, okay, this will be product over I. So this is basically the thing that we did here. For example, here we had these products individually, right? So I just I just wrote the same product using this pi notation. So this follows from like the natural base rule, or yeah, it's basically a topological ordering flow, right? So this is the observational distribution. I hope this definition is clear. We just saw an example. I just wrote the same with some slightly complicated notation. That's it. Yeah, it's not really important for this discussion, but it's just to formally understand what observational distribution. I just wrote this. So this is observational distribution. The interventional distribution is the probability of, let's say S is a set of variables. So here S is a subset of variables, and we are doing V minus S to a particular assignment. So this probability can be expressed by this formula. It's basically the same formula as before, except for the fact that this is Vi in S as opposed to Vi in B. Yeah, this has to be like AUJ, sorry. AC. So this is the interventional distribution. Yeah, so even if this formula is unclear, it is fine for this discussion. I just wanted to like write it formally. We will not use this formula as such during this discussion. Okay, so next I will introduce identifiability. So before formally defining what is identifiability, I wanted to explain a little bit using an illustration. So look at this distribution probability of v1 comma v2, and we have somehow estimated this perfectly using samples. Like suppose we have infinite samples from the data, and we have estimated this perfectly. Now the question is, what is probability of v1 given 2 of v2? And we already saw that the answer to this question is unclear unless the graph is like available to us, right? So if this is the graph v1 to v2, then the answer, so let's call this star, then star is equal to probability of v1. And if this is the graph, for example, then star is v1 given v2. This is the graph where both are independent. Then star is basically probability of v1. And if this is the graph v1 v2, where there is some unobservable, so there is a correlation between v1 and v2, but still star is probability of v1. And if this is the graph v1, there is an unobservable confounder. Also, there is a direct dependence between v1 and v2. For example, from v2 to v1. Then star is basically, I mean, I should write it as star is equal to star, but I will write this how it was defined before. So then we cannot do anything. Like, we actually have to do this intervention. So, yeah, probably I think the first 4 parts will be clear to all of us. And the 5th one is, it's not very complicated. So we actually cannot express this formula using the natural, using like star cannot be expressed using any tweaks of the observational distribution. We actually have to do this. So the reason is pretty easy. So this, let me put a box here. Think of this as like think of two models where u is a random coin toss, fair coin toss. V2 just copies u, and so in model 2 also the same thing happens, and v1 will be defined slightly differently between these two models. So in model 2, v1 is said to be the exclusive OR of u and v2, and in model 1 v1 is said to be 0. So because this is exclusive OR of u and v2, and because v2 and u are the same, v1 will be 0 in model 2, right? So therefore the observational distribution, that is the distribution on v1 and v2, will be the same in both these models. However, the interventional distributions are different. The reason is because in model 1, V1 will take 0 always, but in model 2, when V2 is 0 and U is 1, V1 will take 1, right? So this might look like a cheating, but it's actually not. We can actually construct more legit examples with some complicated probability terms to make sure that we can construct two models, like even without this hiding stuff. But yeah, we will not discuss too much into that for today. I just wanted to provide one example to explain this thing. So what is the identifiability question, right? So I just told that we need additional assumption apart from what we see from samples, right? So the identifiability question assumes an assumption along with the natural assumption that we have the data or infinite samples from the data. So the question assumes that we have the observational distribution, probability of P, and also we have the graph G, the underlying graph G. And the question is whether can we possibly determine a particular intervention 2 of S for some assignment. So this is 2 of V minus S and we are observing S. So we are basically forcefully setting a set of variables V minus S to something, and we would like to observe S. And is this in the sense this factor uniquely determinable from the available information? This is the typical identifiability question. So this uniquely determinable is also called as identifiable. I don't know why it is called as identifiable, but that is how it's called in literature. And this is the basic identifiability question. And more general version of this question would be to ask the same question for so instead of this V minus S, this will be substituted by some other set of variables T. So this V minus S is like intervening everything else apart from what we observe. But a more general case would be to write something like this, where S and T are disjoint sets of observable variables.
So
This is
just a
the
question, like,
yes.
hello.
Yeah, I'm unable to hear
Yeah,
you.
sure.
Sorry.
So sorry. So, just a question, like, so can we, so this is a question of identifiability, like, so you have two assumptions. The second assumption that you know the graph. So under that assumption, can we not identify the effect of every intervention? Because, so let's say like if I knew the graph, then in the effect of intervention will just be like I have to condition on all the confounders and integrate them using the do calculus rules, right?
Yeah, that is true. But we may
So,
have unobservables as confounders, right?
okay, so the
So we
question
just
is
saw
that.
this example.
Mhm.
Yeah, go ahead.
Okay, so the U is unobserved. Okay, so we're dealing with
Yeah.
unobserved confounders. Okay.
So here, for example, we knew the graph, right? So in
Yeah.
this example, we knew the graph, but still we were unable to determine this, right? I mean, I just showed
Okay.
like two models, yeah, which agree on the observations, but do not agree on intervention, the required intervention.
I see. But I think like the V1, the interventional effect of intervention on V2 can be captured as V1 condition on V2 comma U and multiplied by the probability of U as well. and marginalize over U.
Yeah,
So
but U is unobservable, right?
yeah, sure, okay.
Yeah, so if we could somehow observe the unobservable, then yeah, then sure, we will be able to do that.
Okay, sure. Thanks. It's clarified now.
Thank you for the question. Okay, so the question of identifiability is well defined, I hope. And okay, so next, next I will explain C components, which is a crucial definition. So C components are defined as follows.
Saravanan?
Yeah, Vinod.
Yeah, there's one question in the chat.
Yeah.
Can you see that?
Yeah.
Okay.
Does uniquely determinable means parent of A given to of A prime is the same distribution for all A prime. So for this identifiability question, it doesn't really matter what the A prime is. Yeah, so the values doesn't really matter. So it's the same distribution for all A prime. No, that's not what uniquely determinable means. So A prime is given to us, and whether can we determine the probability of A given to of A prime? That's the question. Uniquely determinable in the sense like, do we have like a unique probability of A given to of A prime for the corresponding for the given observational distribution and the graph? So in the sense like from the available information, like can there be a unique probability of A given to of A prime? If it's not unique, meaning like there could be two different P of A given to of A prime that could arise from the given information. Meaning there could be two models, which is in this example, there could be two models where like both these models have the same available information, like same information as the available ones, but the required quantity is different across those two models, right? So it's not possible to uniquely determine which one is the correct answer, right? Because there is a dilemma, there is a conflict.
Yeah, I guess another way to say it is that, I mean, this PAS do ABS is a function, right? It takes values of A B minus S and it spits out the probability of AS. So you give AS and A B minus S as arguments, and the function returns this probability. And so this function is uniquely specified by P, V, and G, right? That's what you mean?
Yeah. Okay, so yeah, I will just so I need to define this function definition C components before getting into the actual algorithm. So let G be a given causal graph, and any connected component induced by bidirected edges is a C component. It's basically the typical graph theoretic connected component. So but C doesn't stand for connected here. So C stands for confounded. But okay. So it's basically the typical graph theoretic notation for connected components, except for the fact that we need to look at only the bidirected edges. For example, look at this graph. V1, V2, V3, V6, and V4. I have to define what a bidirected edge is, but I will do that like in a second. Yeah, so this is the graph. So what do I mean by bidirected edge? So these recall that these unobservables have exactly two children and they have no parents, right? That is the definition. That is from the definition of how we defined our models. Okay, something happened. Yeah. So there is this means that there is an unobservable u1, there is an unobservable u2, there is an unobservable. Just replace these unobservables by connecting both these children by bidirected edge. It's just a notation for convenience. And now like replace all the like remove all these directed edges and look at the graph with only bidirected edges. So then v1 v2 and v3 v6 and v4 and v5 alone. So these are all C components. Even v3 v6 is also a C component based on this definition. Yeah, there are like multiple ways to define this, but yeah, this is fine. So basically it has to be like connected by bidirected edges. But however v3 and v4 are not, because v3 and v4 are not connected by bidirected edges like within that graph. So this is not. So basically there should be like a bidirected path like within the component. So it's the typical connected component, yeah, using these bidirected edges. That's it. And okay, so now we move on to the third part. Okay, so we don't have too much time. Yeah, we have like 15 more minutes. Probably I might take 5 more minutes maybe. Okay, so here we will discuss several observations. And the first one is like I would like to state this theorem 1. And this theorem says that let W be a subset of C and C is a subset of the observable variables, an improper subset. And if W is an ancestral set, I have to define all these things, but let me write down. In G of C, then Q of W is equal to summation V. So I have to define, I remember that I will have to define several things in order to understand this theorem, which I will do right away. So first I need to define what this Q function is. So the Q function is the one that we used for intervention. So this interventional distribution can also be referred by Q of S. So it doesn't really matter what this assignment for V minus S, right? A sub V minus S. It doesn't really matter what that A is. Like, I mean, like for this identifiability question, like that A could be anything. So we kind of skip the notation A within this Q of S. But yeah, this is what the Q of S means. So this Q of S is like a very, very important definition. And yeah, I would like to take a pause here to kind of memorize this definition, because otherwise I guarantee that we will be lost. Okay, so now this Q of S is well defined, and other definitions are like straightforward. So ancestral set in the sense, so W is an ancestral set. Graph G, here it's G of C, but G means W is equal to ancestor of W in G. So by ancestor I mean observable ancestors, only the observables, because we don't really care about unobservables. They are represented using bidirected edges. And so the unobservables are like, they make sense, they are very useful, but they're kind of meaningless when we write these notations. So W is an ancestral set in G of C in the sense. So this is the graph G of C. So this is the typical graph theoretic notation, which is the induced graph on C, the induced subgraph of G over the variables C. So this is G of C and this is W, and W is an ancestral set, meaning there are like no such incoming edges. Like there could be unobservables, but there are no incoming edges from observables to W. This means W is equal to ancestor of W, right? And therefore W is an ancestral set. So if this is the case, then Q of W can be expressed using this formula. And this theorem is like pretty straightforward in the sense that so because there are no incoming edges from these variables to W, it doesn't really matter what we observe here in these dots. It doesn't really matter whether we observe or do not observe. So we can just marginalize over all those variables. Still, it's going to be the same. Like it doesn't matter whether we observe. So here we observe those variables. Sorry. Yeah, here we observe those variables. In C minus W. Here we intervene on the variables C minus W, but it doesn't really matter whether we observe or we intervene. We can just when we just marginalize, it's going to be the same. So this intervene on C minus W, is basically a meaningless intervention. So it doesn't really matter what you do on C minus W, the distribution on W is going to be the same. That's the intuition behind this theorem. It's a pretty straightforward theorem once we understand the definition, I guess. Any questions? Okay, so now we move on to our next theorem.
C is a C component or it's some arbitrary set?
Oh, C is some arbitrary set.
Okay.
Yeah, C is some set which is a superset of W and subset of observables. Okay, so now we will look at another theorem. So all these theorems that we will describe, they all come from Tian and Pearl 2002 result. So this is a kind of important theorem. So this theorem says that let H be a subset of observables, and let H1, H2 up to HL be components G of H. Then this is why I wanted all of us to memorize this Q definition, because once you understand this theorem is like straightforward. Okay, so what does this say? So V is our observable set, okay, and H is a subset of V. Okay. We are interested in the causal effect of these variables dots over H, this box, the inner box, right? So basically split this H into like the partition, the C component partitions, and for each of these C components, think of this as like a connected component. So it will have parents, right? So once these parents P1, P2, P3, let's say, so once these parents are set to something, P1 equal to small p1, small p2. So once these three variables are set, for example, here there are like three parents and there are like three variables. This is the C component. Let's say Hi, Hj, Hi. Yeah. So once these three variables are set, it doesn't really matter what the other variables are. So the distribution on these three variables is going to behave the same, because this is the C component. There cannot be like any other variable that have a bidirected. This is impossible, because otherwise this variable would be inside the C component hi. So such dependence by confounders cannot happen, and also this cannot happen, because otherwise this variable in the square box, this would be a parent of this. So once the parents are set, the behavior of the C component is like kind of fixed. So this Q of hi is in some sense it means this is probability of hi given duo of V minus hi, right? So this is in some sense means it exactly means duo of parents of hi. I'm kind of abusing the notation, like this parent is like observable parents, but I hope that's clear. So now like so yeah, with this understanding we can kind of see the intuition behind this result, right? So this is a famous formula called as C component factorization, and then the second result is yeah, slightly complicated to describe. So this result yeah, so instead of writing this result I would better write it in an informal way. So the Q of chi for all i's can be computed from Q of h. This is what I wanted to say. So Q of hi can be determined from Q of h. So if we have Q of h, then we will have Q of hi. So there is a formula which I am not going to write. And what the number one says is that Q of hi's will determine so if we have these Q of hi's, then we will get Q of h. So the second point says if we have like each of these Q of hi, sorry, if we have Q of h, then each of these Q of hi's can become computed using a formula. So it has like two results which are like kind of which kind of interchange the right hand side and left hand side. So this is the high level understanding of theorem 2. And now next I will explain a lemma. Let me call lemma 1. And yeah, so all these results are like useful and they all culminate in our algorithm later. So let A subset of P be subset of V. So this lemma says that Q of A is computable from Q of P in the graph G. So typically when we don't use this subscript notation, this means that this is like in the original graph G. Okay. If and only if Q of A is computable from Q of P in the graph G of P. So this might look slightly complicated to understand. Just to describe this difference between Q of B in G and Q of B in G of P, like look at this graph V1 and V2. So here we have an unobservable confounder U between V1 and V2, which can also be indicated by bidirected. It doesn't matter what the notation is. So here Q of V2 in G is unidentifiable from the observational distribution. This is what it means by unidentifiable. So let me write it this way. But however, Q of V2 in the graph G of V2, which is basically the isolated vertex V2, identifiable. So because we are looking at only this graph. So these two are like different questions. Like so here G of V2 in the sense like we look at the graph induced on G of V2. I mean induced subgraph induced only on the vertex V2, right? So then Q of V2 is identifiable because Q of V2 is actually probability of V2. Because we are looking at the graph only on V2, we completely ignored V1. So the definition of Q of V2 will be different here. This is actually P of V2. But here this is P of V2 given 2 of V1, right? Yeah, so this is the difference between these two notations and yeah. So all that I want to say is that this is a very crucial lemma. Like in the algorithm, like there are like set of reductions, and like this lemma is like applied in multiple times. Okay, so yeah, it's kind of a bit non-trivial, but yeah, once we understand this, then we can proceed to the actual algorithm. Like once this lemma is clear, then everything else is kind of trivial. Okay, so we don't have too much time. So what I will do is I will write the algorithm and kind of explain it in a hand wavy fashion. So the algorithm is as follows. Identify CTQ so the input to the algorithm is C is a subset of T of N. Q is basically Q of T and GT and G of C both composed of one C component and either written Q of C Q or written phi. And there are three cases. Let A be yeah this is kind of explained now, but yeah I kind of skipped a few things, but yeah I'll just give a flavor of what happens in the algorithm. See, this is a recursive algorithm, so we will call this identifier function. Yeah. So this is actually not the complete algorithm, but yeah, just to give the flavor. So here the question is, so essentially what happens is that, okay, so we need this, right? So the question is, the identifiability question is Q of S identifiable? ID, I will write identifiable as ID from Q of V, right? This is the actual question that we want to understand. So this question is reduced to is Q of Sj's identifiable from Q of Cj, where Cj's are some C components. Okay, so basically what happens is that, like, from this Q of J we can be determine Q of Cj. This is using the theorem that we saw before. Okay, so we know now we know Q of Cj, and from Q of Cj we need to determine Q of Sj, where S is decomposed into S1, S2, etc. up to Sl. So these are all C components into C components, S1 to Sl, and the question is like for all J. So this question, this first question, boils down to this second question: is Q of Sj identifiable from Q of Cj? And this question boils down to, is Q of Sj identifiable from Q of Cj in the graph G of Cj? So this is kind of from the lemma that we had seen before, which is this lemma that we had seen, right? So here this B is the Cj and this A is that Sj. So this G of B is the G of Cj that we have here. And yeah, so now we have this, and okay, I need space. Okay, so now define this so this C that we have it here, right? This is the Cj. Sorry, the C is the Sj, but okay. So like this is the actual question that we are interested right now, and the solution to this question is as follows. We will have we will define A to be ancestor of Sj in the graph U of C. And the first point is, if f is equal to Sj, then so this is basically Sj is an ancestral set, and because Sj is an ancestral set, we can use the lemma that we had seen before. We will be able to write not Cj, Cj minus Sj Q of Cj, because Sj is an ancestral set, where we actually use this lemma, that theorem I wrote. So here I wrote, right, W is an ancestral set, then we can express Q of W as this. So here Sj is an ancestral set, therefore we can express using this formula, and we can determine this required Q of Sj using Q of Cj, and we know Q of Cj from Q of V here in this box which I had drawn. So then Q of Sj is identifiable, and once all these Q of Sj's are identifiable, then Q of S is identifiable based on this formula that we had seen in this theorem, this one. Once these Sj's, which is the Hi here, once these Sj's are identified, then Q of H, which will be the Q of S here, then we can identify Q of S, and that will solve our question. But what if F is not equal to Sj? Then what would happen is that F would be equal to Cj. So in the sense like Sj, and this is the ancestor of A is equal to ancestor of Sj in the
Sorry,
graph.
where do you define F?
S is basically what we want, right? Q of S.
F is Q of S. Okay.
Yeah, S is Q of S, and Sj's are like C components of Q of S, C component partition of Q of S. And now we are looking at this graph G of Cj, and A is this set. This is A.
Hello, Sarvanan.
Yeah.
So isn't it F equal to A? I mean, F you mean actually A, right?
Oh, sorry, F is A. Yeah, in the paper it is F, but I didn't like F, so I changed it to A, but I forgot to change. Thank you. Yeah, so yeah, this is the diagram. So Sj is a small c component, and A is the ancestor of Sj in this graph G of G of Cj. This is the graph we are interested in. And the first thing is like this dots, right? These were empty set. That is case 1. And case 2 is A is equal to Cj, which means this this box which I will draw in green color now, or okay, red color now. This is A. This red color box is actually G of Cj, the entire graph. So that is the second point. So in this case, they proved that. So this is the contribution of this paper. In this case, they proved that fail in the sense Q of S is unidentifiable from the observational distribution P of V. And the third case is when so it's exactly this diagram. So when Sj is a subset of strict subset of A, and A is a strict subset of Cj, then we can perform some so then yeah, then this requires like a step-by-step thing, which I think I will probably skip for now. I can discuss offline if people are interested. So basically what happens is like then this recursive step happens, this final step. So like okay, on a high level, what happens is like suppose Sj is contained in C component. Let's call it H prime, and this is in the graph G of what? G of A. So what this means is that okay, let me draw this diagram precisely. So this is A, and this is our Sj, right? This is Sj, and let me use another color, blue color. So this here set is called as H prime. This is basically a C component. H prime is a C component. In the sense there are no bidirected edges like these. These are like not possible. So then what happens is that Q of Sj is computable from Q of H prime in the graph G if and only if Q of Sj computable from Q of H prime in the graph G of H prime. So this is from lemma what is the number we used? This lemma. This is lemma 1. Again, we will use lemma 1 here. And, yeah, so basically we will try to see if this Q of Sj is identifiable in this particular graph in blue color. That is the H prime graph. And if that is identifiable, then we are good. And if that is not identifiable, then we are not good. This is based on lemma 1. So therefore, we will be able to determine whether this Q of Sj is computable from Q of H prime in G or not. So here we use this lemma 1 as a factor. And this is a small subroutine which is basically this final call. Output identify this final call, and this will result in either of these two base cases. These two are the base cases. Yeah, on a high level, like this is what happens in the algorithm. Yeah, I skipped is like a little bit of details and intuition and proof, but yeah, this is the high level detail.
Okay, that was fantastic. Thank you, Sarvan.
Thank you, Arnab, and thank you everyone for listening.
Yeah, I guess if there are questions.
So in your algorithm, T1 is what? T1 is the C component containing, like what you said.
Okay, so here, okay, give me a second. Yeah, so T1 is H prime because C is contained in C component T1, right? So T1 is the H prime. Yeah, I mean, like I actually didn't prepare to write the algorithm this way, but because there's lack of time, I just copied the algorithm from the paper. But yeah, T1 is H prime and sorry, A is A, T is CJ. Yeah, C is SJ. Yeah, I think pretty much that should be it. I think, right?
Yeah. Thank you.
Thank you, Sutanu.
So is there a concise formulation of what the identifiability condition is, like combinatorially?
I mean, we can enumerate and figure it out by this logic. I don't know.
There is no kind of like forbidden structure or something which says that.
So there is this paper by Spitzer and Pearl, which I mentioned at the start. So in Spitzer and Pearl, they actually came up with a condition called as hedge. So Spitzer and Pearl and this paper are essentially the same paper. I mean, the question of interest is the same, and they provided conditions.
So the paper,
It's called as hedge.
ultimately the algorithm is the same or it's different? I mean, like between.
The algorithm is the same because this algorithm was from Tian and Pearl 02, right? So the algorithm is the same, but how we view the algorithm is different because the construction of Spitzer Pearl requires that hedge structure, but here these people, their construction is different, so they didn't have any structure. They instead like did it like brute force.
I see. Okay, thanks. Okay, anyone else?
Thanks for a great talk. I have a small question. You assume that the input to your for the identifiability, there's a graph on observable variables which is given, right?
Yeah.
What happens if, I mean, are there any known results when the graph is not given?
Yeah, that's a great question. when the graph is not given, like with the additional assumptions, yes, there are results that I am aware of. But without any assumption, I don't think there will be any result. But yeah, I don't know exactly what variants of these assumptions have been studied precisely. But yeah, for identifiability without graph, I am not aware of.
So what does that question mean exactly? Without a graph? I mean, like, so
Yeah, without a graph.
what is the characterization in terms of?
So without graph, for example, learning the graph is a question, right? It's a different
Yes.
question with different assumptions like CI, conditional independence test, and so on, so on. So yeah, people have worked on that, right? Arnab?
Yes.
Yeah, no, but I mean, like, identifiability, what does that mean? I mean, here, I guess the question is, I mean, you want to characterize for which graphs you can identify versus which not, right? So, the graph is kind of the parameter that you are ranging over, and you say for these classes of graphs you can identify, whereas for these classes of graphs you cannot identify. So I guess, I mean, if the graph is not the parameter, there should be something else that you're, that you will use to specify whether it's identifiable or not, right?
Yeah, but the graph could be different, right? For example, the graph could be the graph need not be the actual graph. The graph could be some Markovian class, for example. I don't know what the specific name for that is. Like, I mean, it's
essential
basically
graph.
What is that?
It's called essential graph if there are no confounders. But go ahead. Yeah.
No, not the confounders. What I'm saying is basically a class of graphs together
the equivalence class.
Equivalence class, yeah, Markov equivalence class, right? So so there are variants of such variants identifiability have been studied, but yeah, I mean, like yeah, such variants that I'm aware of, but apart from that, I'm not sure.
Do you remember by any chance the name of any paper?
I mean, so there is a chain of paper by Pearl and their collaborators and students, right? So that is what I am aware for this area. I mean, yeah, if we could just search all those co-authors, and we will be able to get a good set of a good idea of this literature.
Thanks.
Thank you.
Okay, all right. Okay, great. Thank you again, Saravanan. That was fantastic. Yeah, I think that was, I mean.
Thank you, Arnab, and thank you everyone for listening.
Okay. Okay, all right. So I'll put the video up, and also I'll try to put up like a sort of an open problems web page. I mean, so for like open problems which are suggested by the talks. I mean, so if you have some to contribute, then I mean, please email me. I'll also send an email about that later. Okay, thank you so much. Bye.